Hello my friends, Terry here, and welcome back to this series on being an entropy warrior in thermodynamics. And in this video, we're going to derive and calculate equations for entropy under constant pressure conditions, constant volume conditions, as well as a phase transition. And we're going to do a practice example of each. So let's jump in. We're going to start off with a constant pressure condition here. And to calculate the change in entropy for a constant pressure process, we're going to use the thermodynamic definition of entropy, or the Clausius definition of entropy right here. There's an equal sign because this is for a reversible process, the idealized hypothetical process. And to get here, to get any use out of this equation, we need to know what the dq is. And we're going to do that using enthalpy. Because this is a constant pressure process, we can write, so we'll start off with that, dH equals du plus pdv plus v dp. And if it's constant pressure, then dp is 0 because the pressure is not changing. Now we have this du here, so we're going to substitute in the second law, dq plus dw. So dH equals, and then this we're going to sub in dq plus dw, and that's 0, so this is plus pdv here. Great. Now, what is dw? Well, if we allow for PV work only and no other work, so we're making an assumption here, then if that's the case, then dw equals negative pdv. And this is true for a reversible process. I should write reversible here, because this pertains to the pressure of the system. If this was an irreversible process, then this would be the external pressure, or the pressure of the surroundings acting on the system. But this is a reversible process, so this is the pressure of the system. So we can literally plug that in. dH equals dq, and dw is minus pdv plus pdv. Well, look at that. These cancel, and we're left with dH equals dq under constant pressure. This is a P, constant pressure here. And remember our assumptions, right? We used PV work only. We used reversible work, or at least it's in equilibrium with its surroundings. And now we can plug this in. We have an expression for dq. We can plug it in to our definition of entropy, thermodynamic definition of entropy. So dq is now dH over T here. And we want things in terms of pressure, volume, temperature, things that we can measure directly in the lab. So what we're going to do is we're going to invoke the heat capacity at constant pressure here. And we're going to rearrange this to get dH equals Cp dt. And this is constant pressure, constant pressure. So we can substitute this now. This is our dH into here. So ds equals Cp dt over T here. Great. And this is it. That's basically it. We just need to integrate from the initial entropy to the final entropy, and the initial temperature to the final temperature. And we can't do too much here. This is just the change in entropy. And we can't yank this heat capacity out of the integral because it may depend on temperature. So we're just going to leave this right-hand side as it is, to Cp over T dt. And this is our equation for the change in entropy at constant pressure. Here it is in all its glory. Okay, well, let's use it. So we got an example here, and we'll calculate the change in entropy of the system. This is of a system because there's no subscript indicating whether it's the surroundings or total. And the M indicates that it's the molar entropy, so joules per Kelvin per mole. And when CO2, so we have a gas, is heated at 1 bar from, this is our initial temperature, Ti, to our final temperature, to so from 373 Kelvin to 550 Kelvin, and we're given a Cp. And now this Cp, it's not just a number, it's an equation. But that's okay, we'll just move on, just carry on like normal. So our equation for the change in entropy that we just derived is equal to the integral from Tf to Ti of Cp over T dt. And we'll plug this in. Now, this is an equation, so we'll plug that in as it is. What this says is that this is the heat capacity at constant pressure, and it's the molar heat capacity at constant pressure of CO2, so of the substance, and it's in units of joules per Kelvin per mole. And the heat capacity equation is 22.24 plus 5.98 times 10 to the negative 2, and this means it's times temperature, and the units of temperature are in Kelvin here. So there's no units for this number, and there's no units given for this number, but as long as we plug in Kelvin for temperature, then the heat capacity will be in joules per Kelvin per mole. So that's it. We just plug in temperature in Kelvin, and we get these units back here. Okay, so we'll plug in the rest. So T dt. Great. Now at this point, it's just evaluating an integral. So this is, I'll write it down here, the integral from Ti to Tf of, I'll split this up into two terms. So 22.24 over T plus these T's cancel on this right-hand term. 5.98 times 10 to the negative 2 over, oh no, I just said they canceled. They canceled, there we go. And this is all dt here. So we can evaluate each term separately. So the integral of a constant over the variable is just the constant times ln, 24. And this is ln of t from the initial to the final state, plus, now this is just a constant, so the integral is the constant times the variable from the initial to the final. And we can just evaluate it, so we'll just plug it in. So 22.24 times ln, now T final is 550, so 550 Kelvin over 373 Kelvin, 373 Kelvin, plus, now this is divided by, normally it's subtracted, right? This is ln of T final minus ln of T initial, but, so it would be ln of T final minus ln of T initial, but we're just invoking a log law here, where when you're subtracting two logs of the same base, you can just say it's equal to Tf over Ti. These are equivalent. The difference between logs of the same base is equal to the ratio of the arguments, and make it into one log. So, well, there we go. But this one is subtraction, so 5.98 times 10 to the negative 2, and that'll be from T finals, which is 550 Kelvin, to 373 Kelvin. Okay, so we'll plug that into the calculator. Kind of running out of room here. There we go. Okay, so 22.24 times ln of 550 divided by 373 plus 5.98 times 10 to the power of negative 2. And we'll multiply that by bracket. I better do this multiplying here. Multiply by brackets, 550 minus 373, close brackets. I just want to check to make sure everything's okay. 22.24 ln 550. Okay, I think that looks good. 19.22, so 19.22, and our units are joules per mole Kelvin. So because it's per mole in here, then we can say that this is the change in entropy of the system, the molar change in entropy of the system here. Okay, for this next one here, we have a constant volume process. And for a constant volume process, you can think of it as just like a closed flask, a flask that's rigid, it can't expand, or there's nowhere for the gas to go, or substance, really. But in this case, we'll look at a gas, and we're just heating it up, so the volume is constant here. Now, if this is a gas, and only PV work is allowed, and dW is equal to negative PdV, Again, if this is a reversible process, then this is the pressure of the system. This is an equal sign here. And we're not allowing volume to change, so this work term is 0, this differential of the work. So we're left with du equals dq. And we can literally plug that into here. So ds equals du over temperature. And to get an expression for kind of PVT data, so to speak, we're going to invoke the heat capacity, just like last time. The heat capacity at constant volume is equal to the partial derivative of the internal energy with respect to the temperature, holding volume constant. And we can rearrange this to get du equals Cv dt, constant volume. And we can plug this in to here as before, so ds equals Cv dt over T. And we'll integrate it to get the change in entropy from the initial to the final state, and the initial and final temperature. And it's pretty much as far as we can go. The left-hand side will be the change in entropy of the system. And again, the heat capacity at constant volume, it could vary based on the temperature. So we're going to keep it inside the integral just to be general for now. So this is our equation for change in entropy at constant volume. Let's use this in a practice example, and this is it here. So calculate the molar change in entropy of the system for a sample of xenon that's heated isochorically. So isochorically means the volume is constant, and we're going from V1, oh, that's not V1, T1 of 250 Kelvin to 298 Kelvin, and we're given the heat capacity at constant volume, and a molar heat capacity at constant volume is 3 over 2R. So let's calculate this here. And we're going to start off with our equation that we just derived. So from Ti to T final of CVm over R dt. Oh, not over R, CVm over T dt. And we can just literally plug in what Cv is. So integral to Tf, Cv is 3 over 2R over T dt. Great. Now this is a constant, so we can just pull it out of the integral. And we're really looking at the integral of 1 over t, the integral of dt over t, which is just ln of t from Ti to T final. And again, this is just like the other one, so 3 over 2R of ln T final minus T initial. But when we're, ln T final minus ln T initial, there we go. We'll just move this over here. So delta S equals 3 over 2R times ln of, I'll make it ln of T final over T initial. And we can plug in our numbers, 3 over 2. We'll want to use the R with joules, so 8.3145 joules per mole Kelvin. And ln of, what's T final? 298 Kelvin to 250 Kelvin. Should make these square brackets here. Okay, so we'll just literally plug that into the calculator. So 3 divided by 2 times 8.3145 times ln of 298 divided by 250 equals 2.19. So, maybe we should keep another decimal. 2.19. 2.190. 2.190 joules per mole Kelvin. And because mole is in here, this is the molar change in entropy here. All right, so that's that process. Okay, so this is in infinitesimal form or differential form, but this is not in differential form. So if we integrate this definition here from some initial to final state, we'll get the change in entropy, and T is a constant during a phase transition, but dq just becomes Q over T because it's the total energy transferred as heat. And now we can just literally plug that in. So I'll do that down here. The change in entropy is equal to the change in enthalpy of the transition over the temperature. There. All right, another equation for our tool belt. Let's use it in this example here. So we have the enthalpy of vaporization of benzene is 31 kilojoules per mole. And so this is our delta vap, because it's vaporization of enthalpy, vaporization. At its normal boiling point is 80.1 degrees Celsius. Calculate the change in entropy of vaporization of this substance. So we'll do that. And we're literally going to use that same equation we just used. So it is delta vap H over the temperature. And we're given what the change in enthalpy is. It's 31 kilojoules per mole. And the temperature is 80.1 degrees Celsius. Now we need to convert that to Kelvin, of course. 1.5, and that's in Kelvin. Okay, so we'll calculate that. Kind of ran out of room here in my calculator. There we go. Okay, 31 divided by 80.1 plus 273.15 brackets. 0.0, there's only 2 sig figs in the numerator, so 0.088 is all we need, right? 0.088, 0.088, and this is kilojoules per mole Kelvin, and it's kind of not the nicest number to report it as, so we'll just change it to joules. The change in entropy of vaporization is times it by 1,000 to get joules. So 88 joules per mole Kelvin. Okay, and then without looking at a table, this makes sense because there's a rule called Troughton's rule. And Troughton's rule says that the change in entropy of vaporization for a substance is approximately 85 joules per mole Kelvin. And most substances follow this rule here. Some deviate due to intermolecular forces like water and ammonia and whatnot, but most of them are kind of up and down around this value here, Troughton's rule. So, all right, so yeah, that's it. We have 3 new equations in our tool belt for calculating entropy from this video of 3 different processes. We have a couple more equations from the last video and then a couple more from the first one. So we're becoming entropy warriors, and I look forward to seeing you on the next one. Cheers.